Let's look at this problem that asks us to compare the acidity of two different molecules. Being able to compare one hydrogen versus another in terms of its acidity and being able to determine the most acidic hydrogen on a molecule are crucial skills that you're going to need throughout organic chemistry. In fact, most organic reactions have some kind of explanation based on acidity or basicity. So in each one of these pairs, we're going to be breaking down which hydrogen on the molecule is most acidic. We're going to be comparing the most acidic hydrogens between each molecule, and then we're going to be giving some reasoning based on the fundamental properties of molecules. You understand ideas about electronegativity, resonance, size of atoms. Those things may be familiar, but maybe you haven't used them to predict and explain acidity, which is what we'll be doing today. So if we look at that top pair of molecules, on the leftmost molecule, that compound only has one hydrogen. So selecting the most acidic hydrogen on that molecule is relatively simple. On the right structure, notice there's three different hydrogens. In this case, though, each one of those three hydrogens is exactly the same. So picking any of the three would be fine when we're trying to compare one hydrogen on the right molecule to a hydrogen on the left molecule. So in terms of acidity, we only need to compare the most acidic hydrogens in order to determine which molecule is considered most acidic. The molecule on the left has 3 chlorines attached to that carbon, whereas the molecule on the right only has 1 chlorine attached to a carbon. You know chlorine is one of the more electronegative atoms available. And you know carbon is not necessarily very electronegative. So for every carbon-chlorine bond, we know that chlorine is pulling electrons toward itself through that bond from carbon. We know chlorine is more electronegative, carbon is less electronegative, so chlorine has that increased desire for electrons compared to carbon. So almost think of it like a tug of war of the electrons in that bond between carbon and chlorine. Since chlorine is more electronegative, it wins that tug of war with the electrons in the bond. This fundamental property using electronegativity is called the inductive effect. The inductive effect states that the more electronegative atom can pull electrons toward itself through bonds. So if we look at the two structures on the top, we've got 1 chlorine in the right drawing and 3 chlorines in the left drawing. Each one of those chlorines is pulling electrons away from that central carbon. So what's this mean as far as the acidity of those two hydrogens? Well, remember, acidity is highly based on the stability of the conjugate base. So the conjugate base of the left-hand drawing, which has 3 chlorines attached, and then the conjugate base of the right drawing, which only has 1 chlorine attached. Now some of you may have already been thinking as I was drawing this that carbon has 3 bonds and a lone pair. Since carbon only has 4 valence electrons, that must mean this carbon is negatively charged, as well as this carbon. So these are the conjugate bases of those two molecules. Remember, the strength of an acid is based on how stable that conjugate base is. So the more stable the conjugate base, the more acidic the hydrogen. So these carbons have negative charges. Carbon is not necessarily happy with the negative charge, as it's not an electronegative atom. So any way that we can spread out that negative charge is going to stabilize this conjugate base, and thereby mean a more acidic hydrogen. The chlorines on the left-hand molecule are pulling electron density away from that negatively charged carbon by the inductive effect, and thereby making that negative charge more distributed. Whereas the molecule on the right, its conjugate base only has one chlorine. So by the inductive effect, it's only able to pull a lesser amount of electrons away from that negatively charged carbon. So ultimately, the compound on the left is more acidic, because the conjugate base has 3 electron-withdrawing chlorines pulling electrons through those bonds, which is called the inductive effect. So that conjugate base is more stable than the conjugate base of the right-hand molecule. So the reasoning we just used is the inductive effect. Let's move on to the next example. And remember, these examples are usually chosen, whether you're working problems in your book or in practice exams, are chosen in a way so that it brings up different fundamental properties that you're asked to apply to solving these problems. So the top one, we used electronegativity and the new idea of the inductive effect to predict the stability of those two conjugate bases, and thereby predict what's most acidic. On the next problem, remember our first goal is to find the most acidic hydrogen on each structure, and then we can compare the two molecules based on acidity. In this case, like the last, we've already bolded the most acidic hydrogens. But if you weren't able to pick out the most acidic hydrogens on either of these compounds, this is a case where you could apply the pKa table. Oftentimes, hydrogens attached to oxygens and nitrogens are much more acidic than hydrogens attached to carbons, because nitrogens and oxygens are more electronegative. In this case, we've got one hydrogen attached to the nitrogen in the left structure, and one hydrogen attached to the nitrogen in the right structure. The difference between the two is that the left structure has an extra carbon between the nitrogen and that aromatic ring that we see on the left-hand side of the molecules. So does this change the acidity of the hydrogen on that nitrogen in the two compounds? So again, the easiest way to predict which is more acidic is to look at the stability of the conjugate bases. The molecule on the left has a conjugate base that looks something like this. Remember, conjugate base meaning that it's lost its hydrogen. The conjugate base of the structure on the right looks like this. So both structures have a negative charge on nitrogen. Nitrogen, we know, is a reasonably electronegative atom, so a negative charge is better than if it were on a carbon. But again, any charge, negative or positive, needs to be spread out in order to be stabilized. So if you can take a negative charge, in this case, and spread it out as much as possible, then you've got a more stable conjugate base. Remember, we did a similar thing using the inductive effect through bonds in the first example. So in these two structures, the leftmost conjugate base has carbons on either side of that nitrogen with a negative charge. There's no way that we could distribute those electrons on either side to spread out the negative charge. We would also say that this molecule has no resonance forms. However, the molecule on the right-hand side has a conjugate base that allows us to spread the electrons on that nitrogen, causing the negative charge, into the ring. So what you would need to do in this case are draw some resonance forms to show how the negative charge could be spread across the molecule simply by moving electrons. So let's show some of this distribution of electrons. This is also called delocalization of electrons. Basically, we're just trying to spread out these electrons in the negative charge on the nitrogen elsewhere. First, we could take a lone pair and put it into a double bond between the carbon in the ring and the nitrogen. Of course, that makes the carbon in the ring have 5 bonds, so we'd need to relieve that by putting a lone pair of electrons onto the carbon shown there. And then we can show the result by its resonance form, which would look something like this. So notice this structure now has a negative charge on that carbon. Of these two resonance forms, the top resonance form is definitely a better definition of a molecule, because we know we'd rather have a negative charge on a nitrogen than a carbon. But still, being able to show this distribution or delocalization of electrons means that that negative charge on that nitrogen is much more stable than the nitrogen that's on the leftmost structure, if it had a negative charge. So for these reasons, the rightmost structure would be more acidic. So the reasoning behind this right molecule being more acidic is that it's got a more stable conjugate base. Why is the conjugate base more stable? Because the electrons on that nitrogen that's causing the negative charge can be distributed to other carbons in the ring. We showed one place where the negative charge could be distributed, but you could actually draw 2 others showing the negative charge on different carbons in that ring. So the basic idea behind this is resonance. Moving down to the next example, we've got H on a Br, which you might know as hydrobromic acid, and then H on a Cl, which we know as hydrochloric acid. So which of these two are more acidic? This might be a little bit more familiar, so you might be able to predict which one is more acidic than the other more easily. So if you looked at a pKa table, or if you just remember your experience from Gen Chem, you might have known that HBr is more acidic than HCl. But the really interesting thing is when you try to explain that. Because most people's first inclination would be to say that the Br is more electronegative than the Cl. But looking at an electronegativity table, we obviously see that chlorine is actually more electronegative than bromine, which means that chlorine would have a greater desire for those electrons in that HCl bond. So that means that electronegativity does not explain why HBr is observed to be more acidic than HCl. One thing that we haven't figured in is, again, looking at the conjugate bases of the two compounds. So let's look at the conjugate bases, bromine with a negative charge, and then chlorine with a negative charge. So just like the top 2 examples, if we could somehow spread out that negative charge so that it's not locked in one position, then we'll make a more stable conjugate base. Bromine with a negative charge is a much bigger atom And so those valence electrons, where that negative charge is coming from, are much farther from the nucleus, and therefore are able to distribute those electrons over a much greater space. Chlorine is a smaller atom, and therefore the electrons are locked into a smaller spatial area. So because bromine is bigger than chlorine, it's got more space to stabilize that negative charge and spread it around. So that means HBr would be more acidic than HCl. And again, the reasoning behind that is the atom size. Of that bromine. So 3 examples, 3 different fundamental properties of molecules or atoms, all of them based on explaining why a conjugate base is more stable. And if you get even simpler than that, all of them are based on how we can distribute or spread out a charge. The final example, again, now we have multiple hydrogens on these molecules. So first we'll have to pick out the most acidic hydrogen. In this case, again, they're bolded for you. And remember, hydrogens on heteroatoms are usually more acidic. If in doubt, you can always check the pKa table. So let's look at the 2 compounds that we have here. I'm not going to draw the entire molecule, but I am going to draw the most crucial part of the 2 conjugate bases. So here's the conjugate base of the leftmost drawing, and here's the conjugate base of the rightmost drawing. So in these 2 compounds, we've got a negative charge on a nitrogen, which is attached to a C double bond O. And we've got a negative charge on an oxygen, which is attached to a C double bond O. So which of these 2 would be happier with a negative charge? This is a familiar concept. You're used to thinking of the idea of electronegativity. So the oxygen, which is more electronegative, would rather have the negative charge, whereas the nitrogen, which is less electronegative, would be less happy with the negative charge. So which of these 2 would be more stable? It would be the oxygen with the negative charge. If you look at the 2 structures, you probably notice that the rightmost drawing is a carboxylic acid functional group, whereas the left-hand drawing is an amide functional group. So this is just a clear distinction of why a carboxylic acid, and the hydrogen that we're talking about, is more acidic than the amide. On both of these molecules, as a side note, you could draw a resonance drawing by pushing those electrons on either the nitrogen or the oxygen up toward the oxygen in the C double bond O. So I'll let you look at that and see if you can understand how both of these molecules have resonance. But the explanation of which is more acidic solely rests on the electronegativity of oxygen and nitrogen. And again, the reasoning behind that is electronegativity. So 4 examples, 4 different determining factors in why one of those 2 compounds in the pair would be more acidic. Granted, you could use a pKa table to have made all these decisions, although pKa tables often don't have every possible molecular structure within the table. But here we were able to apply simple ideas based on the stability of the conjugate bases of these compounds. The inductive effect, resonance, the size of an atom, and electronegativity are going to be reasons that you'll see coming up over and over again throughout explaining why different molecules behave in certain ways.